So for this one, I'm going to post the code that I wrote, so you can kind of like check your work or whatever.
Cool.
But for that, you should have found that the motion vectors in the x and y direction were around 0.5. As you increase the window size, well, so initially you probably got something maybe around, I don't know, 0.54, 0.56, 0.58, and then you increase the window size, and there should have gone down somewhere close to 0.5. They probably never got to 0.5, but somewhere close to that. So yeah, that was basically the goal. And I think that's all I can say about the project, really. I already posted the second project, which is block matching, and we're going to talk more about that today. And then I want to go on to background subtraction. And yeah, that's the plan. So let's get started with the block matching, or continue where we left off with block matching. So let me see if I can find where I was. Okay. So I have a PowerPoint actually. I want to show you the PowerPoint first. So the question about block matching, and somebody asked me about this last time, whether or not it was practical and useful, and the answer to that question is definitely yes. You need some modifications to get there, but as a starting point, it's actually pretty good. Okay, so I went through the pain of creating this animation here, and we have these two images. The guy is running across the screen. We captured two images of him. So first thing is to downsample and smooth. So I talked about that before. One of the reasons we do downsampling is because we have we're able to reduce the error. If you have a noisy image, for example, and you do downsampling, you got to smooth the image first, and then after that you're able to calculate the motion. When you're taking derivative filters, if you're going off the flow, you definitely want to. We saw that in the first project. So after you downsample and smooth the image, you have these two. And in this case, I'm only going to consider two levels. Obviously, you can have as many levels as you want in the hierarchy. But for two levels, I have an adjacent image and a current image. And it doesn't matter which direction you go in terms of using this as the reference image, and using this as the reference and that as the adjacent, it doesn't matter. So the first thing I do is for the current reference image, I divide it into blocks. We talked about that before. And if I look at just the center block here, so let's say that I want to find this center block and this adjacent image. So I form a search area. And my search area is really big here, but may not be that big in general. And within that search area, I'm going to try to find the matching block. There it is. Let's see it again. So I'm doing a spiral search here, right? And I'm trying to find the matching block, and I stop right there, right? Because this block here matches the guy's arm over here. And so now I have one motion vector. And I need to repeat this for all the other blocks. I repeat that process, I get some motion vectors that look like this. Okay, so I put down here assign motion vectors. The next step I'd say is something called energy minimization, which we're going to talk about that today. But you'll notice that the motion vectors are corrected once I do the energy minimization. All right. So if we assume that everything in this image is moving, including the background, everything moves, then these are the motion vectors that we should see. All right. If it's just the guy moving and not the background, then those motion vectors are not correct. But if everything's moving, then that's what we should see. So once I have those, so this part right here we're going to skip, but it turns out that once you have those motion vectors, you can actually create smaller blocks inside that, and then you copy those motion vectors into the smaller blocks. This is a part of the algorithm that I added. This is not part of the general algorithm, but this is definitely something you can do. You perform energy minimization again on those motion vectors, and then you're going to pass those motion vectors to the next level. All right. So that's what I did here. I just took those, passed them to the next level, and from that next level, you take a block, for example, and that block points to some position over here. You need to form another search area. So maybe you're asking yourself, why are we doing this again? Well, the reason is because when we go from this image to this image, we interpolated, right? When we interpolated, we actually, or maybe we didn't interpolate, we started with the original image and we went down. So this image has more information than this image. It now has extra pixels. So whatever motion vector we found up here is close, but it's not precise. So we're going to move it around just a little bit to be able to get the precise motion vector that we need. Okay, so once I do that, I search that area and I assign motion vectors. Okay. So what the reason I have it shown like this is that for the parts of the image shown, you're going to be able to find some good matches over here, right? So for this block right here, you can see there's a little bit of black up here, so you'll probably be able to find that over here, because no other part of that has that. All of the blocks that I've shown have some part of the guy in them, so you can be able to find those blocks over here. But the problem that happens with these blocks where there's no motion vectors, where I haven't shown any motion vectors yet, because for those blocks, you're going to have this randomness, because they can match anywhere. Like this block here, can match anywhere over here in this white area. So for those motion vectors, you get all this randomness, and we want to get rid of that randomness. And we do that with energy minimization, which I'm going to talk about today. And once I do that, I can break this into further blocks if I need to. I can pass it up to another level if there's another level in the hierarchy, and that process repeats. So that's the overview of how the block matching algorithm works. All right, so we'll go into the details now. Any questions? Cool. All right. So we left off last time. Let's see. All right. So what I had was I started with some image. Oops. Very sensitive today for some reason. This. So here's image 0. There's no way to. That probably is. add some other image one. It's still pretty slow. Okay, and we need to choose one of these images as being the reference image. So we're going to assume at this point that we calculated the motion vectors for the entire image. So let's say that image 0 is the reference. And in the project that I posted, you're going to be calculating the motion from image 0 to image 1. So it's not a bad idea for example to consider that image 0 is the reference. So for this image here, we're going to break it up into blocks like this. We've already calculated the motion vectors. So we have some motion vectors. We have these motion vectors for image 0, and they point to some blocks over here in image 1. So given these motion vectors, we want to pass them up to the next level. And the next level is going to be a bigger image. Okay. And over here in image 1 is a bigger image. Alright, so let's divide this guy up then. Okay, so if these blocks here are 2 by 2 in this image, they're going to be 4 by 4 in this image. And what we're doing is we're just assuming that this big block, this 4 by 4 block, takes on the same motion vector as the 2 by 2 block. That's just an initialization. That's not saying that that's going to be the case, because we're going to actually do another search to find the best block. So all of these guys are going to be the same, except the length of the motion vector is going to be twice as long, right? Alright, so what this means is that these motion vectors now, for example, maybe the first block, I'll use a red here, maybe this block will, you know, I drew the arrow like that, which is bad because the block's going to be outside the image, but let's just say the block goes somewhere over here, right? So then, once the block ends up here, I need to form a search area over here. So this will be the search area. Okay. And then you're going to search over there to find the better matching block, hopefully. Okay. So let's see what else I'm going to say. Alright, so if the search area initially, we had a search area over here, which was, let's say maybe 6 by 6 search area, was the one we used to initially calculate the motion vectors. Then over here in this image, your search area is only going to be 3 by 3. Okay, but the big but here is because each one of these blocks is going to be divided into blocks of 2 by 2. Okay, so in this image over here, you're actually finding a block that's 2 by 2. I didn't show that, but these blocks are 2 by 2. So in the higher level, you're reducing the search size by 2 every time you go up. And that's what makes this fast, is because you're not searching over a ton of blocks and huge search area like I showed before. Alright. So if it's not clear to you why that's true with the search area, one of the nice things to do is just to take a simple image. small image. 2x2 image, 3x3 maybe. I can get this pen to work for me. So you guys, hold on. Let me try to save this and close this program and see if that helps. Yeah. All right. All right. So if we have a let's just say for this 3x3 image, I have a block, just a block of 1 pixel, all right? So for this 1 pixel, if I want to search over this entire thing, then my search size is going to be 3x3. You can see that because I'm just, I need to search 1 pixel in this dimension, 1 pixel in this dimension, and the current pixel. So it's 3 that way, 3 that way, in order to search all of this. Okay. Now, what happens if I interpolate the image? So if I do an interpolation here, so that means that this 3x3 image, we multiply it by 2, I'm going to interpolate by a factor of 2, so this is going to become a 6x6 image, right? So I don't remember if I showed you guys how you actually would draw the interpolation. So let me just, I think I mentioned it really briefly last time. So these 3 are the, or these 6, sorry, 9, these 9 pixels are the original pixels that are in this image. Okay, so the way that the interpolation works is it's going to insert some new pixels. And these new pixels are going to be put like this. So all these little triangles here are the new pixels. So what that means is that this pixel right here, this single blue pixel, is actually going to cover all of these guys. All right. So what it means is that for that new pixel, I only need to search 1 in each direction with that. All right. Because I only need to search over those new guys that have been added there. That's where the whole search size reduction comes into play. So you start with a, what do we start with, a 6x6 or whatever, and then next level will be 3x3, and so on, 1x1, or 1.5 by 1.5, whatever. Right? So yeah, so that's how you continue in this fashion. So generally you would want the search size to be an even number, right? Otherwise it's kind of weird. So this is be like 1.5 by 1.5. That's weird. So you would try to start with 4x4 and then make it 2x2. So definitely choose. It's going to be to your benefit to use the even search sizes and even block sizes. And in the project, I'm going to go through it later. I gave you the search sizes and the block sizes. And these ones are pretty good. I mean, they're not optimal. It's really hard to choose a search size and a block size that works across like a lot of image sequences. You really need some like adaptive way to choose those. But for our purposes right now, we can use some fixed block and search sizes, and we're going to assume that the images are VGA. And the images that are provided to you are VGA images, So those search and block sizes that I gave you, they work well with the VGA images. Okay. So I think you kind of understand at this point where the motion vectors come from, how we find these motion vectors. The next thing that we need to do is we need to talk about regularization. So, going back to that whole PowerPoint issue, can't really show it over there. Is Apple copied the Mac on this because we did like the old versions of, I don't think I can show you, but basically on the Mac, the main screen will show you the PowerPoint slides while you have it up here. So I think Microsoft copied Apple on that. Anyway, so this case right here, when we go from those random motion vectors to something that looks nice like that, we need to talk about how you get those. Anyway, so regularization, let's talk about that. Okay, so let's take the case where we have two images. So here is our reference image, and this is I usually call it the adjacent image. And for the reference image, I'm going to divide it into blocks. And after I go through the block matching step, for each one of these blocks I have a motion vector. So what I'm going to do is I'm going to put most of them going in the same direction. And I'm going to have one that's messed up. Why is it messed up? Only because I'm telling you it's messed up. There's nothing obvious that would tell you that this is the wrong one. This could very well actually be motion vectors that you get. Those could actually represent the real motion of the object. If you imagine that there's a really small object that's sitting in here, and it's moving, a little small thing that's moving in this direction, everything else is moving in that direction. That definitely could happen. For example, assume that the background is moving. So all of these motion vectors around here represent the background moving,